All right, what's going on, you guys? Another LeetCode video today. This problem is called implement trie or prefix tree. So they basically just want us to implement this data structure called a trie. So a trie is a prefix tree. So it's pretty much it's just a tree, right? But its application is for we could see here it's used in things like autocomplete and spell checker. You pretty much have the first letter of a word that you're storing in the tree at the root node, and then every subsequent child node is like the next character in a string sequence. So let's take a look at what that means. So we're gonna, for our trie, we're gonna have a root node. So we'll just have a root node here, and basically what's going to be in here is a array, and this array is going to contain 26 different elements, where each element is basically a node pointer. So it's going to have 26 node pointers here. And each one, and the reason why there's 26, by the way, and not an unlimited amount or a larger amount of characters, because literally in the constraints here for this problem, we could see that the words and the prefix that we're going to be passing into our trie structure are at most only going to consist of lowercase English letters. So we can safely have an array of 26 different possibilities here. So A is going to have a pointer, B is going to have a pointer, C is going to have a pointer, and those are all going to correspond to their own nodes based on whatever the letter is here. So like if this letter is, let's just say, there can be up to every letter in the alphabet, A through Z, but let's say we have A. A is going to have its own pointer, right? And then the structure just repeats itself. There's another, at the next character after A is going to be the next tree node. It itself is going to have an array of 26 tree node pointers, and each one of those is going to correspond to a letter A through Z in the same fashion, right? So there can be up to 26 pointers basically at each node, and that's if the trie got like really, really full. In this example, like the input output it gives us, like it's not getting very full here. Obviously it might get pretty full in some of their some of their trickier automated test cases, but nevertheless, yeah, this is pretty much in sum what a trie is. So hopefully that kind of makes sense. I know it's a pretty like quick explanation, but I think it's pretty straightforward. Yeah, let's get into the code. Let's get into the implementation of it, and then we'll talk about the time and space complexity of each of these methods as we write them or after we write them. So anyways, yeah, the first thing we want to do before we do anything is probably write a struct for a trie node. So we could also implement this trie node as a class, but I'm going to do it as a struct. So we have a trie node. It's going to need to have that array of 26 trie node children, right? So we'll call this children. It's going to have size 26. We'll just have a C style array. And then we also need, we need a marker at each node, basically to indicate if it's the end of a word, because one of these methods, our search word method, only returns true if the string is a word. So you can imagine, you might have a string like mad or something like that, but the whole word is like maddening or something. You wouldn't want to, you could find mad in the trie, but it won't actually technically be a word. So there needs to be a way basically to indicate where words end, so we know like exactly which sequences in the trie are or which paths in the trie are words, right? So long story short, yeah, we need an is word marker here. We can just use a Boolean for that because it's literally just a binary, yes or no. So we also need to do the constructor for this. So we'll say try node and actually initialize these. So to initialize those children, we'll just use a auto loop. So for C for in children, we're just going to set each one of those to null pointer at first. And then we also want is word to be false by default. So that's it for the trie node struct. So to initialize our trie, well, we actually need a root trie node pointer to a root trie node, right? So let's just say trie node star root for that root trie node, and then we need to, in our constructor, initialize that. So we're just gonna have root equals new trie node, and it doesn't take any parameters. It automatically initializes all those child pointers to null. So that's it for the constructor. We also need a destructor because anytime we use the new keyword for a new trie node, we've got to have a way to destruct it. So let's go ahead and actually implement that destructor right now. So so the way you do a destructor in C++ is use that little tilde, and basically every time this class an instantiation of this class falls out of scope, the memory will call this function and then clean it up. So we're actually, the best way to do this is probably to use recursion. So let's actually write a recursive clear function, and it'll just take a trie node, and we're gonna seed that recursion on just the root node. So we're gonna call clear on root. And what we wanna do is, let's see, we want to loop through all of those children, right? So for auto, and actually let's use a, just so I know exactly, what we're altering here, I'm gonna use a C style for loop. So I is less than 26, I plus plus, and then, so we're just looping through all of the children. So we're gonna say if the tree node children at I, so if the ith child exists, right, and just to be really exact here, it does not equal null pointer. So if it exists, if it's not null pointer, and I guess it might honestly just be better to say if it exists at all. So if it exists at all, then we're going to call the recursion on that node, right? So we want to clear children I if it exists, right? Just call the recursion there, and then after we're done looping, and this little line is a little too long. I'm actually gonna indent that, and honestly, this one probably can indent that too. Don't want it to have lines that are outrageously long here. So anyways, yeah, we'll have we're gonna clear like that, and then we're basically just gonna delete that tree node once we're done clearing, or once we've called a depth for search to clear each of the children. So and we're only calling that recursion when the child is not a null pointer. Otherwise, there's no point in freeing that space. So that's going to be our recursive function. Basically, it's going to clear up all of the space we're using for our trie. So let's do the insert function first. So if we have a string word that they give us and we want to insert into the trie, well, we're gonna need a way to traverse down the trie, right? So let's make a trie node and point that to or assign that to whatever the root is pointing to at first, and then let's just go ahead and just loop through word. So for auto C in root, and we could also use C style for loop for this, but I feel like the code is a little more readable when you do it this way. And I think this makes a copy every time. We don't necessarily want to make a copy, so let's just take that by reference. We're not going to be altering it. So for each character in, and I said root, that doesn't make any sense. For each character in word, we're going to want to basically check, okay, if our tree node because we basically want to see if the child, so we need to index into that children array, and the way we're going to do that is we're going to take C and subtract it from A, basically to normalize that character, that lowercase English letter, to a integer value for indexing into this array. So we're going to see if this exists already. Or if it doesn't exist, right? Because that's the case we care about when we want to actually create a new trie node, right? So if it doesn't exist, we're going to say we need to create a new trie node. So we're going to say, and we need to create it where that child is. So tree node children at C minus A. So at that character's index, we want to create a new trie node. Okay, and then we can just, whether or not we made a new trie node, we want to set the tree node to that child, just to move down the tree to the next character. So we do that, and then at the very end of this, void insert, this should be good actually. It shouldn't be anything else we need to do here. So that should handle inserting the word. Actually, there is one more thing we need to do, right? We were talking about this variable, right? So we need to be able to know when the end of a word is. So we would need to set that to true basically here for the final node in this word of the trie. So once we're done iterating, we're going to set is word to true, and that'll just indicate that there is a word here at the end of this final letter. So that's it for inserting. So the time complexity of this, so we'll use TC for time complexity, is going to be big O of in, where in is the length of word. And for space complexity, there shouldn't be any extra space complexity here. That should be constant. So, I mean, obviously there's space with the trie itself, but the trie itself is going to have, let's see, well, let's make a comment of that maybe in the constructor. So it's going to have this space complexity, SC, is going to be big O of M times N, where M is the average length of word, and then N is going to be average or longest length of word, and then N is going to be the actual number of words in the trie, right? So that's the space complexity for the trie. But the time complexity for inserting a word is just going to be N, where N is the length of a word. So we also need to implement a search function and a starts with function. But notice these methods are kind of the same, like the search, there's only a small difference, right? So search is gonna basically search for a word in the try, and it's gonna return true if that exact word is in there. And then starts with is only gonna return true, well, it's a more broad function, right? It's gonna return true if that prefix is in there at all. Right, so really just the difference is search is only going to return true if that word is in there exactly as that word. So thinking about that, we can actually kind of combine these. So let's write a different function called, or kind of a catch-all function for both of these, and then we'll just alter it a little bit in both of these for to make it work. So anyways, yeah, let's call this function, let's return a try node, a pointer to a try node, because we need to know basically if the last try node indicates that there's a word. So that's what we're going to return from this function. So we're going to return a try node, and let's just call this maybe find. Search starts with, yeah, let's just call it find. And it's going to take, let's see, we want to accept, yeah, let's just accept a string, right? So we're gonna accept a string, and we'll just call it, S, and let's accept that by reference, so we don't have to copy it. Okay, so we have our signature now. Let's go ahead and we need a try node, right? Because we've got to be able to traverse down the try. Let's call it tree node, or try node tn. Tn short for tree node. Or try node, and let's set that to the root. And then we're just gonna loop through all of those children in the current tree node or try node we're at. So, or actually, yeah, we're gonna want to loop through the children in the current try node we're at. No, actually, we want to loop through the characters in string S. Sorry, so we're gonna say auto and character for string S, by reference, or again, we're not copying the character, and we're just gonna say if not, because we want to see if this character is not in the try, right? And if it's not, then then it's safe to say the word isn't going to be in here at all. So we can just return like a null pointer. So if not, try node children C and then -a just to get that proper index. So if that doesn't exist in the try, then it's safe to say that we can just return null pointer, because this word is not found, right? So otherwise, we're going to, if it is there, because that's what we're looking for. We're looking for when it's there, then we can update try node to that child, just to keep moving down the tree and keep searching. And then after that, we're just going to return the last try node that we end up at, to determine if it's to determine whether or not it's actually a word, or if just the prefix is there. So for search, we actually care if the word is there. So let's have a try node called, this is like the end of the word, right? So we'll just call it end, and we're gonna call find on word, right? So that'll return basically the last either null pointer or the last try node if it exists, right? So if end and end is word, then only then can we return true, right? Otherwise, we're just going to return false. Okay, and then for starts with, we really only care if end, right? So we can literally just say return, well, it could be a null pointer, so we have to say if find prefix so if that's null pointer, then we're gonna, and we don't even need to, it's like a bit verbose, right? We don't even need to like do that equality. So if find prefix, we can just return true, otherwise we'll return false. And that's pretty much it for this. This search and starts with, I mean, obviously these functions are on the outside are just constant, so we really just need to look at the time complexity of this find function, which is going to be, again, it's going to be the exact same as insert. It's going to be linear with respect to the length of words. So, and that kind of, this function basically, you know, works behind the scenes for both search and starts with functions. So yeah, so let's go ahead and submit this. Yeah, so hopefully this video, you know, helped you understand the problem better. If it did, leave a like and subscribe, and I'll see you guys in the next piece.